for having me here. It's a beautiful exercise to get over here in the morning from the Berkeley area. It's nice, really nice walk. So anyway, I will be talking today about model reduction techniques. In our case, we are working on the downfolding and quantum flows. Those two things can talk to each other. They are especially important from the point of view of making realistic simulations of chemical systems on quantum, whatever we have right now, right? On quantum computers with still limited capabilities, right? In ground state simulations, we are interested in bringing static and dynamical correlation effects together, right? Without those two components included, we cannot talk about the predictive quantum chemistry. So for some time I was thinking, because the audience is pretty diversified, and there might be mathematicians here, and I was thinking how I can find the analogy in math of what we are doing for the quantum chemistry, right? And I found really nice examples, Grabner basis set theory. So make long story short, you start with the polynomial system of equations, right? And Buchberger algorithm, which is behind the Grabner basis, it's a kind of elimination algorithm on steroids. Actually, the Gaussian elimination algorithm is a specific case of the Grabner basis set applications. So you start eliminating using some lexicographical orders, and at the end of the day, you end up with a polynomial with a single variable, right? And this polynomial in a single variable describe what, in that case, variable z feels as a part of the initial set of the polynomial equations. So this gives you an idea how it works. So we want to compress some information to a small space and basically focus on that. In the quantum chemistry, we are not doing exactly the same thing, but it's a pretty good illustration of what's happening. So we are basically trying to find some effective Hamiltonians that describe our big systems, and you might find different guiding principles, how to design those effective Hamiltonians. And effective Hamiltonians is actually the history behind the quantum chemistry. You go to 1929. Van Vleck theory, Van Vleck approaches. So this is kind of the first attempt to do so, which was followed by many, many developments, not only in chemistry, but also in the material science and physics. So this list is far from being complete, but really intense development of those techniques happened in chemistry starting from mid-70s. What we are doing differently, we are using different ways of looking at those effective Hamiltonians. Originally, they were formed using the concept of the wave operator formalism. Basically, they were designed to capture the strongly correlated states. But what we are doing is different. We are actually using the single reference theory, and we have two classes of those downfolded Hamiltonians, non-Hermitian and Hermitian. Non-Hermitian downfolding is actually encapsulated in the standard single reference coupled cluster theory. Hermitian requires some extension. It's more challenging. It requires more approximations in the practical applications. But those two things show how much actually simple cluster ansatz can, and how much information can encode about the entire system. So let's start from the beginning. So very simple idea. Let's start with the single reference. So we have a active space, right? The active space defines the partitioning of your cluster operator into the internal and external part. If this part, the exponent of the internal part acting on your reference, can generate the full CI type expansion within your active space, then you can show that energy of the single reference standard formulation given by this textbook example can be evaluated as a different way, as an eigenvalue of effective Hamiltonian, shown here, which in a sense integrates out the degrees of freedom used to describe the systems which do not belong to the active space, right? If you like this formulation, you can use the asymptotic case and assume that you have 0 active orbitals. And then you recover, again, textbook example. Textbook formulation. So in this slide, I showed only part of the Kaplan cluster equations. The part of the Kaplan cluster equations which is used to reproduce the energy. But of course, the full Kaplan cluster equations are shown here. The effective Hamiltonian part is only a part of those the Kaplan cluster equations, which defines the subsystem described by some active space, right? So there is the whole rest of the world given by this those equations, right? So this, you can see this first equation as a subsistence with the well-defined effective Hamiltonian, while this part defines the interaction of your system with the surrounding environment and describing the surrounding environment itself, right? So this looks like, depending what part of the equations you are looking at, this part looks like renormalization approach, like in physics. Or if you look at those two system equations as a whole, you can see this as an embedding formalism. So you don't have to do anything here because Kaplan cluster itself is a nice platform to develop the embedding formulations. So this recently triggered those formalisms, this way of looking at the Kaplan cluster triggered a lot of exciting developments in quantum chemistry. So we have Aviciii, Brigitta, and Lin. There's a number of really interesting papers along this line. So a few comments about this. This downfolding, single reference downfolding makes sense. It assumes that Kaplan cluster solution exists, right? What is really interesting, it doesn't care about what that solution represents. In a recent paper which is under review, we show that actually Kaplan cluster theory can provide a mechanism for breaking symmetry. So it can encapsulate or encode the states which are orthogonal to your reference function. So it can see reality beyond given symmetry subspace of the full Hamiltonian, right? And then you start seeing some really contradictory situations because you can form that based on this SES theorem from the previous slides. You can form the effective Hamiltonian in the active space, which, for example, has no quintet components, but describing energy of the quintet state. So this is somehow intriguing to what extent exponential ansatz can encode this information. And this is also a very recent development about the state universal Kaplan cluster downfolding, because right now so far we're talking about the ground state applications, but how we can go beyond the ground state. Can we have similar structure describing excited states? And it turns out this is possible. So in the previous slides, I showed you this form of the effective Hamiltonian. So if you know the exact form of the external amplitudes, cluster operators, you can reproduce the exact ground state energy, right? But here you can go one step further and basically start forming state universal single reference cluster downfolding, right? Which is like oxymoron, right? Because single reference also brings this feeling that you are dealing with a single energy. Actually, it's quite opposite. So using the same expression for the effective Hamiltonian, but the different interpretation of the external cluster operator, you can form state universal effective Hamiltonian, which describes several energies, ground state, for example, and some low-lying excited states, corresponding to the states which are of the same symmetry as our reference Slater determinant, right? So this is very exciting development. So we'll be pursuing those things hopefully pretty soon, especially in the context of the quantum computing. So there are a few interesting things about this downfolding. So we verify it numerically on small system, H6. So this is the CCSD energy obtained with the standard textbook expressions. Then we use several active spaces. In each case, we were able to reproduce the same CCSD energy. This state, this active space is very interesting because it basically does not contain any correlation effect, right? Null, but it's still, you can get the same energy. Here, this is a very exotic excited active space spin orbital, right? So you, in a sense, you are entangling, you find effective Hamiltonians for a single entangled electron with the full Hamiltonian, the same energy, right? So recently it was a big discussion about this no downfolding theorem, and this coupled cluster downfolding does not lie within the domain of this no downfolding theorem. So there's the reason very simple, because in the original paper published by Troy, it was assumed that effective Hamiltonians do not depend on those monodromy parameters. So actually, in our case, it does, because it goes through all amplitudes which define external amplitudes which define effective Hamiltonians. So there are two different stories. And we verified it numerically for our favorite system H2, right, in the non-trivial basis set 4 orbitals, right? But for the all internuclear separations, we were able to reproduce ground state energy using coupled cluster downfolding, as it contradicts the conclusions of the non-downfolding theorem. So there might be something of this sort, but this requires extension of the no downfolding theorem to a more complicated case. We don't know how that would work. But this is actually one part of the ongoing work with Fabian Vollstieff. So hopefully we'll have something soon. So this SES theorem is valid for many active spaces. This is not only one active space. You can form effective Hamiltonian and get the energy. There's a lot of those active spaces, and their number for CCSD theory is shown here, right? It's quite a big number, right? So the question is, what's happening if you start combining those active space problems and you allow them to communicate, right? So by kind of putting them in the form of flow. And you can show that solution of this flow, formalism is equivalent to the solution of the standard coupled cluster formulation, which is approximated by cluster operator, which is a unique sum of the internal excitations used for all those active spaces included in the flow. This opens a little bit new areas, directions in how we construct coupled cluster approximations. So if you take the combination of the smallest active spaces with the one active occupied, one active virtual, you can show that the resulting coupled cluster approach is equivalent to inclusion of OT1s and seniority 0, T2 excitations. I know that I'm aware that the seniority theory is now driving a certain number of the development in quantum computing for quantum chemistry. So, but those flows can also be a nice language to express the locality, right? So you can see that for localized orbitals I and j, you can form the effective Hamiltonian, right? Because you can make active space out of those two, and basically you have those electron pairs, effective Hamiltonian, well defined. But this is no longer a 2-electron system. This is 4-electron system in this case, right? So there are differences in the interpretation. So, but this approach gives you good understanding or good definition of the electron pair at the level of the Hamiltonian, effective Hamiltonian, so you don't have to postulate, for example, the density matrix. So let's move on to the quantum computing and how we are going to utilize those things I've been talking about in performing the quantum simulations of the big systems with the reduced number of qubits. So the first our first attempt was based on the extension of this SES theorem, right? So using this double unitary coupled cluster ansatz. And one has to be aware that this ansatz is exact under certain assumptions. We are assuming here that we are using in derivation this disentangled unitary ansatz introduced by Francesco Evangelista, Garnet Chang, and Gustavo Scuseria. And we are performing those rotations in a certain type of order, right, to get this representation. So this ansatz can be exact, assuming that all the Campbell-Hausdorff, Campbell-Baker-Hausdorff instances of using Campbell-Baker-Hausdorff theorem produce converging many-body expansion. If this is the case, we can very simply derive the effective Hamiltonian, which is Hermitian in this case, but has a very similar structure as for non-Hermitian case. In this case, if we want to do something tangible, we have to basically apply several approximations, certain classes of approximations. We can only deal with the finite commutator expansions. We have to get the source of the sigma external from somewhere. And for the practical reasons, we only keep 1- and 2-body interactions in the effective Hamiltonians. But even though recently we demonstrated quantum hardware simulations for benzene and free-base porphyrin on the ion, on the Quantinuum and IBM in the non-trivial basis sets. So originally 260 basis sets for benzene and 406 for the free-base porphyrin. We chose to deal with the 6 active orbital active spaces, and this is what we got, right? So on H1, on Quantinuum hardware, we're able to reproduce using effective Hamiltonians for this 6 active space. We're able, in both cases, to recover 98% of the correlation energy compared to the CCSD parenthesis T results, right? If you use, for the same system, bare Hamiltonian in the same active spaces, you end up with the 3% and 1% respectively. So this is a good motivation for us to move on in that direction. So this, yet another algorithm I would like to talk about is quantum flows. So let's assume that we want to solve the problem in the space which is too big for us. No hope. But for whatever reason, we know the active spaces, which are components of the target space, which we know we encapsulate important correlation energies. So then you can basically approximate this sigma operator by some cluster operators belonging those active spaces. In general, we assume that those active spaces can overlap. And the trick is in basically looking at the problem from the perspective of the given active space, right? So we decompose or partition the sigma operator into internal part, which belongs to the active space, and the whole rest, and use the Trotter expansion in the way that we leave one exponent of the internal operator to the right. If you introduce this to the energy functional, it looks like whatever is between this and that looks like the effective Hamiltonian, right? And this is the energy of the system felt by the active space. If you were able to perform all those operations in the exact way, all energies should be exactly the same. But given the number of approximations we are using, they might be different, right? But this is the main idea. So this we use, of course, for the simplest case, Trotter rank 1, given here. And again, the form of the effective Hamiltonians felt by the active space is exactly the same as, you know, in the downfolding, Hermitian downfolding. So we can reuse our codes for this case. And there are a few examples. So, sorry. This is H8 in a small active space showing how it converges. We are recording the energy of the most important active space. We are introducing the ordering of the active spaces. So, but here is the behavior of all active spaces, to tell the truth. So we start from 0. We are assuming that we know nothing about the underlying structure of the whatever state. So each active space pings us back the Hartree-Fock energy, and then we start going very close to the full CI energy using 4 qubits in this case, instead of, give me a second, 8 qubits instead of 16. This is where this is the energy if you used if you solve for the main active space only, right? But the software hardware requirements here and there are the same. Here you do it repetitively, right? So quantum flows. Okay, this is yet another example for the more correlated case for the 3 atomic unit separation. So you're a little bit off here. But still, given the hardware resources you have to provide, I buy this result. It's a pretty good result because normally you would end up here, right? So okay, so we are thinking immediately about how we can, because we were solving those flow equations in a kind of cyclic semi-serial way. So the question is how we can use if there is a level of parallelism we can use. And it turns out that doesn't matter which way you execute quantum flows. In serial or parallel, you're getting the same numbers, right? And this is our most recent examples. We have C++, bells and whistles implementation with the Q-flow is integrated with the quantum simulators, UCCSD based on VQE. However, you can use a different type of simulators here, or algorithms. The requirement is that the state vector which optimizes the given active space problem can be translated into the unitary coupled cluster representation. But anyway, using this code, this is work of Nick Bauman and Ajay Paniala, and we integrated our coupled cluster downfolding with the NWQ-SIM. This is our local quantum simulators. We're able to deal with the system defined by 82 active orbitals using 56,000 active spaces, small size, 12 qubits. And in total, we optimize over 1 million wave function parameters, recovering more than 98% of the total CCSD, single reference CCSD energy. So this is for the propane. We have another example here. Before I finish, this is water in the different basis sets, starting from CCPVDZ to CCPVQZ. So we are using a similar approach with the 6-orbital active space covering to some extent the Hilbert space, and we are able to play with the CCPVQZ basis, a very realistic basis set corresponding to 114 orbitals. Again, those are differences between the quantum flow based on the UCCSD solvers and the CCSD total energy when all orbitals are correlated. So right now we are thinking about integrating this with the quantum hardware. So where only the most important active spaces will be optimized on the quantum hardware, right? The rest will be done in an alternative way, right? Because right now we cannot do the 56,000 active spaces on the quantum computers, but we are thinking about utilization of the quantum hardware for the active spaces, which uniquely triggers the sought-after state, right? So we think there will be a huge role played by the machine learning methods here. Another example, Hubbard models, but I will skip over that. Conclusions. So the most important information about quantum flow, we can tune to the existing hardware and basically provide algorithms which are expressed in terms of the constant depth quantum circuits. So this is probably the most important. It's a good target for the parallel parallel quantum computing, possible extension to the time domain. As I said, machine learning might be used to optimize the choice of the active spaces for the quantum flow. So this is a team of people who are working on that. So we have domain scientists and computer scientists, and as well as the QAS experts. This was my last slide, so hopefully we have a few minutes left for the, yeah, okay.
Yeah, plenty of time for questions.
Thank you, Karol. So is this all for systems with, you chose small systems, but what about when you have strong correlation and you might need a multiple?
So yeah, so
state?
basically this is, this is a very good question. So basically, this is how we deal with the dynamical correlation effect, right? We wanted to only demonstrate that there is a way how we can bring the dynamical correlation effect to the game, right? But I agree with you that this is somehow limited to weekly and.
No, I just wanted to ask: do you see a way forward with?
Yeah. This is that's why I'm flipping the
correlation.
I'm flipping the slides in the reverse time order, right? Okay. Here, right? So we have extension. We will build the extension of the Q flow based on this state universal effective Hamiltonians, right? So this give us a much better kind of control over the strong correlation, right? You are not entirely, limited by the form of the coupled cluster amplitudes. Which you are using for construction of because solutions might not exist or might not be accurate for the very challenging cases, right?
I have another one, if I may. So do you see, so you have a very large optimization problem that you say that is very nicely solves goes very well on the quantum computer up to certain sizes. So do you see possibly a role for machine learning in just replacing this all by a classical optimization with neural networks?
Well, yes. I mean, there are I would say all things I was talking about are agnostic to the choice of the technology, right?
Right.
If we have things ready on the quantum side, let it be. But yes, machine learning, this is where we also going, talking about machine learning. So we introduced recently, for example, the VNet, this neural network to produce the effective Hamiltonians based on the bare Hamiltonian in the active space, right?
Yeah.
So this might be an interesting case for the machine learning to contribute to this type of thinking, right?
Yeah.
But this is not only forming the effective Hamiltonian using ML. There's something more, and this is what we call tangent model, which goes back to the old Van Vleck perturbation theory. So we published with Chao Yang the paper where we demonstrate that machine learning and neural network can identify certain features of the effective Hamiltonians,
yes,
which were postulated in 1985 in chemistry by Shai Shavit, and 4 years later in nuclear physics by I don't know, I don't remember the author, but this is very well-known nuclear physicist, by Kubo, I guess. Yeah. So there are multiple layers where the machine learning can be used. Also on by, for example, optimizing active spaces. For example, which active spaces should be integrated, or which should be executed on the quantum hardware. So there are many layers how the ML and AI can be used there.
One quick question.
Yeah, thanks for the really nice talk. Actually, I got one mathematical question about the downfolding. I was just curious about after you derive this effect Hamiltonian, is there any way, like for example, for the couple cluster to derive a bound to estimate the difference between the H effective and the original H?
So you're asking about the differences, right?
Yeah.
So this is part of the answer to Birgitta's question. So in general, we know little about the difference for the single reference theories. But there are, in the past, there were papers postulating some functional dependencies between bare Hamiltonian and Hamiltonian obtained from the Van Vleck perturbation theory, which is very similar to multi-reference couple cluster formulations, unitary couple cluster formulations. And they were coming from the two different angles, right? Nuclear physics and quantum chemistry. So I believe there are some similarities worth exploring further, right? Because Shai Shavit stopped at showing, hey, this is the functional dependence between effective and bar in the bare Hamiltonian in the active space. And then he switched to, of course, to the perturbative analysis. But with ML, we can build the models which can be designed by those kind of theoretical or analytical dependencies, right? I don't know if this answers your question.
Yeah, thanks.
Mm-hmm. Let's thank Karol on the side.